right, our next speaker is Zhuoran Li from IMAX. He received his BE degree from McMaster University in Hamilton, Ontario in 2017, and his PhD. He received his BE degree from McMaster University in Hamilton, Ontario in 2017, and his PhD from the Department of Electrical and Computer Engineering at the University of Waterloo, also in Ontario, that is Canada, in 2023. He's currently working as a research scientist at IMAX and has research interests in video perceptual quality assessment, video encoding, and video streaming. And today in his presentation, he will introduce a study that they performed at IMAX of a comprehensive framework for holistic content quality evaluation that considers both display technology characteristics and also the human perceptual experience. I'm very excited to hear more about this, so please welcome Zhuoran.
Okay. Thanks, Mac, for introducing me. Today I'm gonna give you a presentation about the recent work we have done on preserving the creative intent across the displays. It's objective metric that we have developed recently. So I think many of you have attended the welcome session yesterday, where Lawrence Sher got interviewed, and in his technology vision list, he wished that in the consumer side, the TV can automatically adapt the most according to the content that is played. And at that time, there was a little thought experiment happened in my mind. What if that in the future someday, like the Amazon Kindle e-reader has this kind of movie mode, sports mode, that allow the content creator to play videos on them. But we know that it's not possible because the display capability is limited. It's currently only display the white and the black colors. And on the other hand, what if like some content creator just want to display the black and white Kindle book? So it means that it is a good display hardware that can display that kind of content. So although my thought experiment is a little bit extreme, but it some kind of includes the motivation behind our work is that the first one is preservation of creative intent. The creative intent of filmmakers, they treat it as art. They want the delivery pipeline to faithfully preserve the content at the very end, like the consumer side of the TV consumer side. But there are challenges. The first one is that the various process with like compression, color space conversion, and color gamma conversion, etc., can introduce significant distortions, like altering the originally intended visual experience. But even if we have a perfect delivery pipeline, there's always at the end, there is always a display and this TV panel. So in addition to the previous challenges, every TV panel has a unique physical limitation that can further degrade the visual quality, leading to common distortions like bending, skin tone deviation, color shift, and loss of details in shadow, in highlight, etc. So then there is a need for the accurate assessment of like how much is this deviation for the TV from the reference monitor that is used by those content creators. So to ensure that what consumers see on their TVs closely matches the filmmaker's original intent, it is essential to develop objective model that can assess how well the creative intent is preserved through the consumer TVs. Yeah. So then this one is the outline of my presentation. Firstly, I will talk about some background knowledge, and then the introduction of my of the problem, of what problem I'm gonna solve, and then I'll talk about the proposed method. And for the third step, I'm gonna talk about the subjective experiment we have done to verify our proposed effectiveness of our proposed method, and then I'll talk about the results, like a statistical measure of our comparison of the proposed method result against the subjective experiment. So yeah, so this one is a simplified version of the content delivery pipeline. So firstly, after the capturing of the camera, then the video content are sent to the studios to do editing or color grading. And then after the color grading, it is the videos are going through, sent to the distributors to do the packaging and transcoding. And in the end, like I said, so it is the device that play a key role on the viewers' viewing experience. So yeah, so the viewing device plays a key role in creative intent preservation. So previously, we have been in talk with AIC, and they give us a list that the cinematographer's top concerns of what kind of creative intent are included. So on the top of the list is the skin tone. As for the yesterday, today, many people talk about it, and also includes the shadow details, highlight detail, banding, color shift, and texture. So that are the classes like under this creative intent. So they are most concerning with. Although the objective metric we designed here is not is a totally new metric, and there is no right now there's no available metric that is totally comparable with our proposed method. But right now there are some quality metric that focus on the compression artifacts, claim to be like display aware. So for those kind of compression quality metrics, it can be classified into two categories. The first one is that the first category is to adjust the quality model prediction by incorporating the viewing environment factors and use these factors as a post-processing step. But there are some limitations to this kind of method. First, it only takes considerations of the display device technical specifications, such as how large is the screen, and what lighting is it viewed, and what's the distance are you watch those screen. And it fails to account for the actual physical process of the content rendering. For example, how the light is emitted to the human eyes, and then how the human eyes perceive those lights, those renderings. So it ignores the display capability on color rendering. Yeah. And there is the second type of this quality metric is mostly the data-driven approach. So what the data-driven approach is doing is to take the available subjective rated dataset, video quality dataset, and jointly modeling the viewing display and the human visual system. And those kind of dataset are typically viewed at a specific setting with a specific device. But the issue with that kind of approach is that when the new device come, or when you want to test want to design a model that's suitable for a new kind of viewing condition, you have to redo the subjective study. And it is very time consuming and expensive. So it's resource intensive. So here comes to the problem that we want to solve. The ability of different home TVs to preserve the intent of content creators are different, regardless of the quality of the incoming signal. Even if we have the perfect compression quality of the incoming signal, the display would always render it differently. So the goal is to measure the creative intent deviations compared to the reference device, which is used by the content creators. This is a general framework of our proposed method. So when the streaming content is delivered to the consumer side, firstly, we model this. We have two models. For the first one is the model for the reference monitor, and the second one is the model for the test TV. And by using these two models, we can render what's the real physical light will be as the reference rendition and the test rendition. And then we compare the reference rendition and test renditions by using a human visual system driven quality model and give a quality score. So basically, we designed the model for the reference monitor, the test monitor, and then we also designed the quality metric. So I'll dive deep into how we do this modeling for the monitors and the TVs. Yeah, on the right of this slide, you can see when the streaming video is streaming to the home, it is firstly goes through a decoder, and the decoder will decode it into electrical signal, and then it will go through some transfer function, the EOTF transfer functions such as HLZG and PQ. As you can see, these two steps are totally we know how it works. We can treat it as the white box. But the thing is that after it has gone through this transfer function, the output of this white box is the theoretical optical signal, and then it will be piped into the TV. But the different TV manufacturers has different tuning of their TV, and usually this piece of information is not publicly available. So we have to model it as the black box. So we know the input of the black box is the theoretical optical signal, and then the output is the real optical signal. So the real optical signal, we can measure it by the color meter or spectrometer. So basically the model we want, the thing we want to do is to model this black box. Generally speaking, this kind of creative intent metric including two parts. On the right, you can see is the TV photometry model and the geometric model. The geometric model is actually includes the specs and the viewing distance, which is not the part we're going to focus today. The part we're going to focus is the photometry model. So how do we characterize the TV? How do we model the TV? So I think you are pretty familiar. We sample the colors in color gamut, and then we measure how the light is, what the light is emitted, what the color looks like using the color meter. And on the right, you can see how we measure the colors in the left setting. And here are some test patterns that we use, part of the test patterns that we use. And specifically, because we want to deal with the most concerning problem, which is the skin tone. So we did a literature review. We find what region of the color gamut, like where those skin tone colors are reside in those color gamut. So we also put some skin tone color pattern specifically for the skin tone deviation test. And but yeah, so that's how we model the match the monitor and the TV. But in the end, when we display content, those patterns cannot be easily translated to the real content we see. So we did a subjective experiment to verify that if we have a good model for those colors. So we set up 3 viewing devices. There are 2 TV on the side and 1 reference monitor. And the content we use are the STEM2 content from the AIC. And those contents rich with human skin, shadow detail, highlight details. And we take the reference monitor contents as the reference, and we ask the participant of the study to compare the TV displayed content against the reference to pick like which one do you think is better and give a subjective score. So the first step is we verify if there is actually a difference between the 2 TVs. We verify different viewing devices' capability on creative content preservation, and we did a t-test between the display A's subjective score and display B's subjective score. The finding is that display B is statistically better than display A. So the conclusion of this first step is that viewing devices have a significant impact on viewing experience. So here I'm showing some pictures that we captured and for the test content we have. So on the first row underneath is the subjective score we collected, and on the second row is the IMAX metric that we designed. Here is another one. So lastly, we test our IMAX metric performance on the benchmark dataset, which is the subjective ratings we collected. We compare the SRCC, PLCC, and here are the performance results. So that's it. Thank you. Okay. Go back.
Thank you. That was really interesting. I've got a couple of questions before I open it up for all of you guys. The first one is for the modeling of the different TVs. Besides color rendition, do you also take things into account such as like spatial consistency?
Not the spatial consistency, not right now. So we are just focusing on the color, like the skin tone. So that's the first step. So of course, it's we understand the color consistency at different locations is also very important, but it's also actually like we can also incorporate it into our framework. We can like just capturing the patterns on the corners, on the side, like that.
I think even beyond that, if you think about it from remember early on when a lot of these HDR displays came out, you had like this kind of like edge-lit TVs that are able to do HDR to a certain degree, and then you have the tolerate backlighting displays coming out that are a lot more granular, a lot more consistency. And I think a lot of those things probably do have a lot of impact on the viewing experience as well, not just color accuracy.
Yes, that's true.
Are you also testing it? I saw that you tested it in dark environments. Are you testing it in different ambient environments?
That's our next step for testing on the ambient environment, like incorporating the ambient light into consideration. So that's our next step. Yeah. So for now, we are just focusing on, because we want to make it like a good comparison between the studio environment and the viewing environment, because in studio, usually people work in a dark environment to do color grading. So we pick that for the TV, we pick a cinema mode or filmmaker mode to do the objective comparison. Yeah.
Excellent. Any questions out there? There's one all the way in the back and that one over there, actually.
Fred Walls, AMD. So I had a question. So there are a lot of variables in TVs with respect to processing, right? So even expecting them to render a color the same, as the scene changes, for example, the average picture level varies, right? You're going to get different colors out of your TV because TVs take advantage of a lot of psychovisual things, depending on how your eye is adapted and so on. So, what is kind of the end goal here? Is it to create a mode on the TV that is, representative of the creative intent, or is it just to highlight the fact that there are these differences? Or I guess it wasn't clear what the conclusion is.
Yes. So your question is, what's the purpose of this, right? So the thing is that we know that the TV manufacturers, when they are doing the color tuning of their TV, they always use some kind of test patterns. But those test patterns doesn't translate to the content, as I have said in the beginning. So for some content, it doesn't have this skin tone. So which means that for skin tone, but for some contents, it has rich in skin tone. So we want to bridge this gap between the contents and the test patterns, that how this test pattern can translate to the contents, real content that consumers see. So that's the purpose. And also we want to quantify that, because I think most of the TV manufacturers, that's engineers sit in front of the TV and the reference monitor and do the tuning, but there is no quantitative measure actually exists to measure this. So that's also the purpose. Yeah.
Hi. Do you have any plans to think about modeling different types of panel technology? This is going to touch on probably a couple of the themes we've already heard, but if you take your lovely OLED out of the mix and focus on backlit displays, typically you can measure a set of color patches and come to conclusions about color accuracy. But as you say, once you're watching real content, you might be in a very different situation. And it's not necessarily because a TV is doing nasty stuff to a picture, although sometimes that's true. Sometimes it's because it's fighting its own backlight. So within the zone of a backlight, you don't necessarily have the ability to accurately serve all of those pixels, because you've had to decide, I'm going to sit this zone of my backlight around here, and then I need to kind of try and compensate for the pixels that needed to be brighter or darker or whatever. And that's highly unpredictable. It's going to be different between every brand, and it's very difficult to measure. So I'm interested to know how you're thinking about OLEDs versus thinking about other things that have got their own inherent challenges.
Yeah. So, I think what I'm talking about here is just a general framework. So it's in the end, we're going to measure the color. But this measurement, because we treat this tuning and those things as also the backlight thing as a black box. So if we can take a good measurement, like of the what the color is, then we can properly model the whole process, like also taking the backlight into consideration. So yeah.
This is difficult to measure, right? Because it's at a pixel level, not something that you can nicely measure with a colorimeter.
Yeah, at the pixel level. So right now we're just focusing on like not the pixel level, like the general large block. But of course there are some available color. As far as I know, the colorimeter is able to focus on the pixel level. So the colorimeter is so small, yeah, but it's very expensive. Yeah.
Yeah, I think it goes along the question I asked about the spatial consistency, because from a user perceptual perspective, if I'm watching something, like you said, OLED is one thing, all of the other displays with various backlighting technologies, you inevitably end up with some sort of blooming one way or the other. And how do you take that into account? And I think it's a really challenging thing to do. Any other questions? Oh, Catherine.
I wanted to ask a bit about your subjective study.
Yeah.
One of the things that you concluded was that TV B was better than TV A. Can you describe what participants were asked and like what specific instruction they were given to give their quality assessment?
Yeah, so we asked directly, the first question is just because we study the limit our scope to the skin tone. So as I have shown here, the pictures are about the skin tone. So we just asked the participant to rate which TV has a closer skin tone compared to the reference monitor. And then we also asked them to give a subjective score. So from 0 to 100, how would you rate this TV compared to reference? We told him that this reference is like perfect. So, yeah.
Thank you.
Any other questions? I think you have time for one more question if you want to. If not, I will let you all go to lunch. All right. Thank you all so much. Thank you, Zhuoran. I think it's great work, and I appreciate you presenting it here. And you guys all enjoy lunch. Thank you.